Welcome everybody on Zoom, welcome everybody in the lecture hall, welcome everybody from the future. I hope you had a good Easter break. It was actually 2 full weeks without me bothering you with new material. So now 3 weeks later, here we are in the middle of index construction. As a reminder, what we are trying to do is that we covered already the standard inverted indexed and Boolean retrieval, right? So you know now this structure, you've seen it so many times that you know it by heart. And we even programmed it in the exercises. But the thing is, we did it at a small scale. So we didn't really care about performance. We just needed to parse through the text, tokenize, build the index, and so on. And it worked. Now it's good because the approach is always correctness first, and then we worry about performance, right? You should not optimize too early. And now we have to scale because the internet is much larger than what fits on a computer. So we are going to do it step by step. And we are going to figure out how to build this for much, much larger quantities of textual data. So last time, right before the break, I told you about one trick to slightly compress. The difficulty is that while you are building the index, you actually manipulate pairs of term documents, right? Every occurrence of a term in a document basically is a pair. We call that pair A, start with a P, a posting, right? That's the name of one of these pairs. A posting is a pair made of a term in a document, and it means that the term appears in the document. Now, after you have built the index, you no longer see the pairs, because since on every row, these are all the same term, then you don't repeat the term every time in every pair. So all you have is the document IDs, and the term is only just once on the left, right? But in fact, these are actually postings. Now, the problem is that while you build the index, you have these pairs flowing around in your memory. And if every time you have the full term, that can actually take some space. And the trick, it's called dictionary encoding. It's very popular in databases. Instead of repeating the terms every time, we encode the terms with a number. There's term number 1, term number 2, takes a bit less space. And that's called the term ID. And then instead of the term, we have the term ID. So T1, T2, T3, T, you don't even need to put actually. It's just to clarify that it's a term ID. But that's it. So you can actually just store them as integers. And if you want to quickly experiment, this is actually what they did in the textbook. This is without the term IDs, and this is with the term IDs. So what are we computing here? It's what we fit on a single machine, right? Because we're interested in scaling. So we first have to scale on a single machine. How much can we process? Before the term IDs, we were able to process 1,100 million tokens. That's 11 gigabytes of text with a single machine that fits in 16 gigabytes of working memory. But with the term IDs, we can fit more. Now we can fit 20 gigabytes of text, right? So this is an improvement, right? With a very simple calculation. So now let's get to the actual fun of index construction, and let's figure out how we can scale things. Now, here's the things. We have the memory, the RAM, and we have the disk, right? What limits us right now is the working memory. That's our first bottleneck, right? What do we fit in the working memory? Now the disk is much larger, right? We have only 16 gigabytes of working memory, but we might have, I don't know, 1 terabyte or 2 terabytes of disk, right? So you might think, first, why do we care about the memory? Let's just work with the disk, right? Let's just read and write from the disk. We have 2 terabytes, so we can fit much, much more on the disk, right? So you could think, okay, let's just read and write from the disk. And in fact, I even took 12 terabytes of disk, right? I was more optimistic. And now you fit 5.3 terabytes of text, right? So 530 billion tokens. So this basically fits much more, but of course it's a disk, right? So it's much larger than the memory. But you see the problem with that, right? The problem that you are going to have is latency, right? Every single time you will want to read and write from the disk, you will have to wait, right? So this is not, that size is not even an SSD. It has to be a magnetic drive. And so you're going to have the rotating head, and you will have to wait for a few milliseconds every time you want to read and write something. So this is highly inefficient because, yes, you can absolutely process 5 terabytes of text, but maybe you will need a full year in order to do that, right? And that's not acceptable. You cannot wait for a year in order to have it. So you know it's the compromise. The disk is much larger and contains much more, but it's also slower. So what do we do about it? Well, the trick has a name. It's called batch processing. The trick is that if we need to read and write a lot from the disk, because in the end, this is where we will put the index, we just need to do it in a smart way. Instead of many read and writes on the disk, we need to batch these reads and writes into fewer and larger blocks. This is basically based on blocks, right? When you read and write from the disk, you do it in 4 kilobyte blocks, for example, as an order of magnitude. You just don't do it 1 bit at a time. So the trick is to batch process and to write large quantities of data in a single read or in a single write. And that way, you're no longer limited by the seek time, by the latency that you wait. Now you become limited by the throughput, the number of bytes per second that flow to the disk in a single batch. For whom is that clear? That's called batch processing, right? In fact, the term already dates back to older than that. You know that before the computers existed in their modern form, the computer science department did not even exist yet. So computer science at ETH was hosted by the math and the electrical engineering departments. And there were these computers where you could bring your punch cards every day. The doctoral students would bring them there, and they would batch them, right? People would bring, they would accumulate the punch cards in a batch, and then in the night, they would just feed the machine with the batch of punch cards, right? So this is where it comes from. So batch processing is the idea of fewer, larger chunks of data that get written. In order to achieve that, we are going to do something that's called sharding. This collection of documents that we have, it might be a few million documents, a few million books, for which we have the full text. We are going to partition it. It means, for example, that if we have 1 million, we are going to have 100 shards of each 10,000 books. That's one example. Now there's many names. You can call it a shard, a block, a chunk, a partition. There are many splits. There are many ways that you can call that. Comes all from the big data universe. But we shard the collection of documents. And what happens next is that we process 1 shard at a time. Again, that's the idea of batch processing, right? We do it 1 of these partitions at a time. So now, with a single shard, if we smartly pick the size of a shard so that it fits in memory, we can process that shard as if it were the entire collection. We just process it in memory. There's ample space for that in memory because it's only a shard. Then we process the second one, forgetting about the first one. Then we process the third one, and so on and so on. And that way, we are able to scale because we just do it shard after shard, and we can fit much more than what would fit in the memory because we do it sequentially, right? One after the other. That's the trick. And the same for writing back the intermediate results, right? We basically, so if now I zoom in, right? Now, if we are done with the first shard, we parsed, we got the term document pairs in memory, more exactly term ID, document ID pairs. When we are done with that first batch, we are going to write down to disk some intermediate results. It's just what we've done so far to index with the first batch, right? We write it down to disk. But you see, that's a single write, right? So this is much more efficient than if we wrote term ID, term document pair by term document pair. Now we go to the second one. We use the memory for that, and we write it back to disk, intermediate results. Then we process the third one. You write it back to disk. In practice, it will be more than 3, right? It can be 1,000, many, right? And at the end, we have these intermediate results stored to disk. So of course, that's not yet a standard inverted index, But what we will do is now merge these intermediate results, because they are much smaller than the collection. We merge them into a single big index that we put back on the disk, right? So this is the idea, okay? Note that I'm assuming that it fits on the disk, right? So there is still this assumption that my documents fit on the disk and my final index also fits on the disk, right? It doesn't have to fit in memory, but that I will explain why later, right? You can actually stream your way through, so you don't need to fit in memory, but it has to fit on disk, okay? So far, everybody with me? Yes? Okay. So now I'm zooming in. I'm basically diving deeper into the explanation of what I've just said. That was only the high-level explanation. Now, I'm going to zoom in a little bit. This is the first technique, so there's a whole history of that, right? Over time, there were fine-tunings of the process and improvements over time. So I will start with how the first ideas of how this was done. So the early idea is that you take your first batch, it's on the disk, you parse it, and you build your term ID, document ID pairs into memory, right? It's a pair of two integers. It means that you also need to keep track of the mapping between terms and term IDs, right? This is how you know which term corresponds to what integer. So you will need a bit of room in your memory for just that. And this is the whole time across all of the shards, right? From the beginning to the end, you keep track of the term ID mapping. Why from the beginning to the end? Because it needs to be the same mapping. You cannot change the mapping at every shard. It has to be the same mapping over the entire process. So you need a bit of space in memory to do that, right? And then once you've done that, you can fill your memory with term ID, document ID pairs, right? All that fits into your memory. And that's it. Now you have your term ID, document ID pairs. You can nicely, so first you will have them in the order in which they appear in the documents, but then if you sort them by term ID and then by document ID, you have a sorted list. And that's it. And then once it's sorted, you will generate the standard inverted index. Small parenthesis on how we built that term ID, document ID mapping, term ID mapping right there. How do we build it? There are two strategies, two approaches. The first strategy is that you start with that. Before you even start indexing anything or processing the shards, you first do a first pass just to generate the term ID mapping. So you go over the entire collection. You can stream your way through, right, through the entire collection on disk. And then you build your term ID mapping. Every time you see a term, you see if it's already in the mapping. If it's in there, then you don't do anything. If it's not in there, then you add it with a new integer, and that's it. And then you do the entire collection like that. What's important is that the collection doesn't need to fit in memory because you stream your way through, right? You only do it with portions of the collection at the same time. The only thing that is in memory is the term ID mapping. Streaming is just like Netflix, right? It's the same idea that you don't download the whole episode, but only a few seconds or a few minutes at a time. So we stream through and build the term ID mapping. That's strategy one. Strategy two is on the fly. You start with your first shard, and then you build on the fly as the terms arrive in memory. Then you expand your mapping as you go, and shard after shard, you build this, right? So either as a pass on the very beginning, and then you have the complete term ID mapping, you don't touch it anymore, or you do it on the fly while you are processing the shards, okay? So strategy one and strategy two. Parenthesis closed. So now we have this term ID mapping. Now that I have my term ID, document ID pairs, again, these are pairs of two integers, I can sort them lexicographically, first by term ID, then by document ID. I sort them like this. So now you see it's nicely organized. You have all the yellow, let me show you how I mean with the way it's sorted here. Like this, all the yellow terms, then the red terms, then the blue terms, then the green terms, then the purple terms, then the brown terms, right? So it's nicely sorted by term ID and also by document ID increasing, really, even though you don't see it. So you sort it. That's n log n, right? The sorting, just n log n. So you sort everything. And once you've done that, you just write it back to disk, right? You write back your pairs, term ID, document ID pairs to disk, right? Note that there's a small variation here. Either you really write the pairs to the disk, but you see you can optimize a bit, right? You could write, for example, the yellow term just once, this term ID just once, and then the document IDs, but without repeating the term every time. This is yet another way you can slightly compress, right? So there's the two variants for this technique, right? But anyway, we write back to disk the term ID, document ID pairs. And then we're done with our current batch. So we repeat, and then we end up on the disk with plenty of such lists of such sorted lists of term ID, document IDs. And at the very end, we need to merge them, right? You remember merge sort? There are many ways to sort, right? Bubble sort, merge sort, quick sort, and so on. Merge sort is of interest to us, more exactly the second half of merge sort. You remember how merge sort works, right? You basically shard the input, you sort each shard individually, and once you've sorted every shard individually, you merge them. What is the complexity of the merge part? Is it n log n? What's the complexity of merging? Okay, let's vote. Who thinks it's n log n? Who thinks it's O of 1? Who thinks it's O of log n? Who thinks it's O of n? Yeah, we have a majority here. Indeed, it's linear, right? So the merging part is linear. Why is it linear? Well, let's just do that, right? Because what we have here, in fact, is just the second part of the merge sort. So we have this sorted list of term ID, document ID pairs. We just traverse them concurrently, right? So this is all on disk, and let's say I have 3 of them. So I start with the yellow one. So you see all the yellow ones, and then I'm done. This is exactly this idea of the merge sort. Note that now I didn't repeat the yellow term ID. I kept it and just wrote the document IDs that correspond to it, sorted by document ID. Then I go with the red one. I always have my 3 pointers, 1 pointer in every one of the lists, and I compare the value, the pairs that my 3 pointers point to, and always pick the smallest one and append it to the results, right? Now the green one, the purple one, and so on, okay? What's very important to understand, you need to understand what's in the memory and what's on disk. What's very important to understand is that this here is in the memory, the term ID, document ID mapping, the term ID mapping. This is in memory. These lists of term ID, document ID pairs, this is on disk, and I traverse them concurrently, but these are all on disk. What I write back is also going to the disk directly, right? I can do it, of course, in blocks. I don't need to write every single one at a time. I can, for example, do it term by term, but this is the idea. So I read from the disk, write back to the disk. And by the way, when I'm writing back the term here, I can replace it with the term. So if I have a term ID here, I can find the term that it corresponds to and put the actual term in there, right? So the term, the document IDs, the term, the document IDs, and so on. This is linear, right? I just traverse concurrently the lists and I merge them into a single large index. At that point, I kind of have my standard inverted index, right? Because I have the terms right there and the document IDs, the postings lists right there. Who understands how this works? Okay. So you see, now we are able to process much larger collections, even those that wouldn't fit in memory while we have the pairs of term documents, right? So we are able to process larger collections. So the complexity, if T is the number of tokens, so the tokens are the pairs, right? So if it's the number of tokens, it's T log T. The second step is linear. So overall, it's basically T log Now, there's always a matter of how it feels. And in practice, it feels more like T O of T, because the part of log T, you still do it batch by batch, right? So every time you sort only the tokens of a single batch. So this is why basically it has to do with the constants that you have in front of the two steps, right? So this modifies the feeling in practice. I don't know how to express it better than that. Okay. All right. So this is BSBI, right? BSBI meant, you had it, I think, on a former slide, BSBI, never remember it by heart. BSBI, there is somewhere, BSBI, block sort-based indexing, BSBI, right? So this is how it's called, blocked sort-based indexing. Okay. So let me now zoom again. Okay. So historically, that was the first one. Then there was a second generation of indexing. This one is called SPIMI. SPIMI, for single pass in-memory indexing. I usually remember BSBI and SPIMI, but of course, if you also remember what they mean, it's even better, right? So single pass in-memory indexing. It's not so different from BSBI. So as you can see, it's really a generation thing, right? It's just that there are improvements over the first version. So in BSBI, the first version that I've just presented to you, when you process one of the shards or one of the blocks, you end up with these pairs of term ID, document ID in memory. Well, in SPIMI, you are not going to store the pairs of term ID, document ID. Instead, you are going to store mini standard inverted indices, right? So it's equivalent. So it means that when you parse the document here, the shard that you're currently processing, you keep a structure that just looks like the standard inverted index with the terms and the postings list and so on. You just keep adding the postings to the index. And once you're done with the shard, then you have a mini standard inverted index, not for the entire collection, but just for that shard of the collection right there. Note the reason why it's efficient, because the document IDs that you write here, every document has a document ID, but it's in order, right? The shard is made of document. This is document 1, document 2, document 3, document 4, document 5, and so on. So it means that what you do here is only happens at the end of the posting list. You never insert something in the middle. All you have is always the highest document ID you've seen so far. You keep increasing them. So you only happens at the end of this. And maybe you're going to insert a new term. You know that here you can maintain some sort of tree structure, right? In order to keep that. You don't have to go as far as a B plus tree. By the way, you can have a simple tree structure that takes care of it. So insertion is basically logarithmic, right? You've seen that in theoretical computer science. All right. So again, this is in your memory. This is a data structure in your memory with a tree right here and linked lists here, and you keep appending to a new posting to the list. So far, so good. So this is a mini standard inverted index just for my shard. And when I'm done building this standard inverted index for my shard, I write it down to the memory, right? So to the disk. I write it down to the disk, right? So a term, the list of document IDs, a term, the list of document IDs, a term, the list of document IDs, and so on. Okay? But what's new is that when we did that, what we have in our mini standard inverted index here are the terms. We don't have any term IDs anymore. We directly have the terms. The reason we don't need term IDs is that with this structure, every term appears just once. So we don't need the term IDs anymore. We can drop them. That's good because the term ID mapping takes a bit of space in memory. So if we can get rid of that and drop it, we have even more working memory available for doing that, right? Okay. And then at the end, we have all of our mini standard inverted indices, right, that are on the disk. What we do, we merge them. What is the logarithmic complexity? It's, who thinks it's O of n? More hands, more hands. Who thinks it's O of n? It's linear, right? Look, let's do it. So I start with the yellow one. Then in memory, I can merge my two lists. Then the red one, I merge them. The purple one, you see, it's all linear here. It's just merging, 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 because all these posting lists, they are already sorted. This is all in linear time. And now we have our gigantic standard inverted index for the whole collection. Okay? So this is it. And now the complexity is a bit smaller. It has to do with the fact that we don't have to maintain the term-term ID mapping anymore, right? So it means that every shard is standalone now when we process it in memory. So it means that every shard will be m log m, kind of, in the scale, where m is the number of the terms, and t log m because you accumulate over all of the shards, right? So now we have a slight improvement in complexity. Okay, and m is the longer of terms, and here it's kind of cooking, right? It's kind of a bit hand wavy, but basically the log m is negligible compared to the t part. M is the number of unique terms. T is really the part that is much larger, so it's basically O of t in the way that it fits in practice. Okay. So BSBI, SPIMI. Who would be able to program that? See some raised hands. Okay. So this is the idea, right? You shard your input collection and you process one shard at a time. In BSBI, you load the shards into term ID, document ID pairs, maintaining a term-term ID mapping. Then you write back the pairs to the disk, and then at the end you merge. In SPIMI, it's a slight improvement. You drop the term IDs, you drop the term-term ID mapping, you build a mini standard inverted index for every one of your shards, write them back to disk, and then at the end, in linear time, you merge the mini standard inverted index into a giant standard inverted index, and you're done. So this is how it works. Who is with me? Okay. So now we've made some progress. We've made some progress because now we are in a position that we can build a standard inverted index for collections that fit on the disk, even if they don't fit in memory, right? So now we can do an entire disk's worth of indexing. But we're still not quite there yet because the entire web doesn't fit on a disk. If you look at now the entire web and you want to build a Google, you want to build something that indexes the entire web, that's still not good enough. You still cannot do it in this way. So we need a third way to actually construct the index. And that way is using a technique that normally is taught at the master's level. So this is part of the big data lecture, but I'm going to still quickly introduce it to you now. It's called MapReduce. Who heard of MapReduce? Okay. So MapReduce is a big data technique. It was invented at Google. It's already probably 20 years old now. What characterizes MapReduce is a combination of being extremely simple, it's a simple model, and at the same time, it's extremely generic in the sense that it can solve a lot of problems. So it's simple and generic. The idea is that you want to execute some queries. So in that case, in our case, the query is to build the standard inverted index, right? We take a collection, we want to split a standard inverted index. And we are basically processing the incoming data into shards. I told you shards, chunk, partition, it doesn't matter how we call that. These are just partitions of the input data. And the idea of MapReduce is that it has this kind of structure, this kind of pattern. This is the power of MapReduce. So let me show you. Here you have the input. In our case, that would be the collection of books. And here you have the output. In our case, that would be the standard inverted index. The idea of MapReduce is that you process in parallel the shards of the input, one shard, one shard, one shard, one shard, one shard, right? You map them to some intermediate results. Then you shuffle over the data, right? It means that you change the order in which the data is, and then you again process in parallel here the intermediate chunks of data, and then you output the data to the disk. Now, you probably see a few similarities with BSBI and SPIMI because there is kind of something that we've done there. In BSBI and SPIMI, we did have this idea of shards that we processed one at a time. But in BSBI and SPIMI, that was sequential. It was sequential. It was first this, then this, then this, then this, then this. So there was time flowing there. But in the case of MapReduce, that's no longer sequential. That's happening in a data center on 1,000 machines, and this is all in parallel. This can all be done in parallel. Okay? Shuffling around, because we are on 1,000 machines, means shipping data over the network in the data center. It changes the machine, right? It goes from a machine to another machine, right? And then you again process in parallel at the same time in the data center and write it back to disk. This is the idea. So now this is just a more detailed way of the same thing, right? The idea is that you take the input, you have a map function that basically says everything here gets mapped to something else, intermediate results. Then you sort the intermediate results, partition them again, and reduce them again. Now, you know that when you have a hammer, everything in the world tends to look like a nail, right? And what MapReduce does well is that it manipulates key-value pairs. Everything in MapReduce is a key-value pair. The starting data is a collection of key-value pairs. The intermediate data that you shuffle around is a collection of key-value pairs. And the output data at the end is, again, a collection of key-value pairs. So when we say we map, what do we map to what? We map a key-value pair to key-value pairs, right? Every key-value pair gives you 0, 1, or more key-value pairs, and so on. So these are, again, key-value pairs. When we sort here, what happens is that the keys that are the same are together, right? And here, what we do is that this is all the key-value pairs with the same key, the intermediate results, again, key-value pairs with the same key, and then the reduce function transforms these groups of key-value pairs into a key-value pair, right? This is the idea. Now, teaching the details of MapReduce needs probably, I would say, 3 or 4 hours in the big data lecture. So I'm obviously not going to give you all the details. I just wanted you to understand on the high level what it's kind of doing. What better way to do it than to hunt Pokemons, right? So this is how I actually explain MapReduce. So imagine that I went on a Pokemon hunt last weekend and I actually caught plenty of them. And I need to count them. I want to know how many Pikachus I have caught and so on. So this is the result that I want at the end. So I could, of course, count them at home one by one, but it's going to take a while. So what I do in the big data lecture is that I actually bring the Pokemons to the class and I ask the students to do it for real. We actually did it in the lecture hall. And the way that we do that is that I'm sharding the Pokemons. I have little bags. In every bag, there's a few Pokemons. I distribute the Pokemons to the students. So they are volunteers. They get a shard of Pokemons. Every one of the students who got a shard of Pokemons is counting just for their shards, right? So they know here there's 2 Pikachus, for example, and they write down on paper this. These are key value pairs, by the way. The key is a Pokemon. The value is an integer. Then we have the reducers. The goal of the reducers is first they get the intermediate results. These are intermediate results, right? What the first volunteers did when they wrote these Pokemon integer pairs. Then there is a shuffling. It's something, if you could see it for real, basically in the lecture hall, all the students who have their key value pairs, give them to the students who are volunteering as reducers. For example, Alice here gets from the mappers all of the keys with Pikachu. And once she has all of these keys, she computes the sum over them, right, of these intermediate values and write down the final results for Pikachu which is in that case 8, right? So you see, this is mapping, this is reducing. And in between, there's the shuffling. It's a huge mess in the lecture hall when we do that, but this is what happens. And at the end, the output of the reducer students is the final output. For whom is that clear? Okay, now it's fun to do it with Pokemons, but now we have to do it with documents that we want to index, right? So let's do the same thing, building a standard inverted index using MapReduce. So again, you have a hammer, everything must look like a nail, so we need to make the collection look like key value pairs, right? So this is our input, this is our output. Now, this is kind of familiar now, right? Because we've done it with BSBI and SPME, and again with MapReduce, there is again this idea of sharding the collection of documents, but there is a difference. Because in BSBI and SPME, where was the collection of documents? Right here on your laptop, on your hard drive, right? And you shard by just coming up with a strategy for how you are going to divide it. But when you shard a collection of documents with MapReduce, that's in a data center. It means that the shards, they are distributed over thousands of machines like this. How? We'll see in big data, right? But this is basically distributed over a cluster of machines. And then the mapper face, here I put somebody, but in fact, it's a computer, right? A server in the data center. They are going to take documents here. So I take an example with two documents, 1 and 2. And imagine that in the first document, I found 4 terms. I found ETH computer data and information in that document, and CPU ETH information computer in that one. So my mapping function, this is a mapping function here, converts this document into these 4 key value pairs, and this document into these 4 key value pairs. Now in MapReduce, these also have to be key value pairs, but this is easy, right? We can just assign a doc ID and say one is the key and this is the document is the value. There are many ways of doing that. We can also say the document is the key and then the value is just some dummy thing, right? There are plenty of ways of doing that. We could also use, I don't know, the address or some sort of address where it is on the hard drive or some hash or something. But basically, we can make it look like a key value, right? And then here, we get key values, which is a term is the key and the document ID is the value. So now these are my intermediate results, okay? Then there's the shuffling. So all of these term document ID pairs will get shuffled over the data center. They will go over the network wires from computer to computer. But this is all arranged in such a way that all the pairs with the same key, the same term, in that case, information, when they travel over the wires, they all go to the same machine, right? So we arrange that all the key value pairs with information as the key will all go to that machine right here. And then we can build the reduce function. Now, what does my reduce function do? Obviously not a sum, right? Because that wouldn't make sense to sum over the document IDs. That's not what we want. Instead, we want to concatenate them, right? What we want to do is output still a key value. My key will be the same here. So it's the same key that is right there. I keep it. But my value here is going to be the concatenation of this in a sorted fashion, right? 1, 2, 4, 5, 8, 9. This here is my value, right? I can even already put the document frequency. Since I'm at it anyway, I might as well also count them and put the count in there. So you see, intermediate results, term document ID pairs, final results, term postings list pair. For whom is that clear? All right, so this is my reduce. And at the end, what do I have? I have the standard inverted index, right? And it works, yes? Do we have maybe the microphone so the people on Zoom hear you?
Why don't we, in the map, already map that to a small inverted index, and then so that we don't have to repeat document IDs or documents themselves, then just pass the row that is ETH to the first one and CPU to the second.
I think in the way that I visualize it or that I understand it, it has to do with the shuffling phase. Because in the shuffling phase, you want to make sure that the intermediate results are redistributed over the machines. Now, you need to ask yourself, what is the granularity of that? And the granularity of the shuffling is the term, right? You need to make sure that everything that is the same term has to go to the same machine. Now, my intuition is that if in the mapping phase, you would directly generate, like in SPIMI, in fact, right? A single standard inverted index, you would have a single very big key value, right? That has the entire standard inverted index for a chunk. Then you're kind of stuck because how do you shuffle that, right? When you want to shuffle it, you cannot send it anywhere. You would have to cut it again into small pieces to send the terms to the right machines. You see what I mean?
Then you have multiple key value pairs. You can send them, but it's only one key value pair that you send per machine.
Yep. So what you're suggesting is an optimization where you say that, for example, in that case, I could group this information 1, information 2 into a single key value where I have information and 1, 2. What you have described is called a combine function. And this is one of the ways to optimize MapReduce, and you're absolutely correct about that. This is what actually happens in practice, right? But as I said, I cannot do the whole MapReduce lecture here, but this is very clever, and this is indeed the sort of things we can do with MapReduce. And in fact, this optimization wouldn't be specific to information retrieval. That can happen in a lot of different use cases in MapReduce, right? But that I'll cover in the big data course if you come back next fall, right? Okay. Yes, we have another question right there. So it depends on the phase that you're looking at. Oh, the volume was not set, so probably on Zoom they didn't hear you. So the question was about whether the key values are on the same machine if it's the same key, right? If it's the same term. Now, what's important is that in the map phase, that doesn't have to be the case, right? In the map phase, the terms are all over the place because, for example, imagine you have ETH. You could have a lot of documents with ETH, right? So in the map phase, that term could be potentially on every machine, right?
I was thinking about the reduce phase.
Exactly.
Then you want all like the same key to be on the same machine. But what if
yes, exactly. So that's exactly what the shuffling is for. When you shuffle the data, you arrange that all of the terms that are the same, all of the the key value pairs that have the same key, they all go to the same machine. The way this can be done is with a hash, for example. You can compute a hash and everything with the same hash goes to the same machine. What happens in practice is that the machines that map, that compute these things, they will already eagerly sort the key values in such a way that the terms are already together. And what happens during the shuffling phase is that the machines connect to each other and download the right data. So it means that the machine that will be in charge of ETH will connect to every single machine in the network and download the parts that contains what they are responsible for. This is how you achieve that all the key values that have ETH as the key, during the shuffling, they will all go to the same machine. That's how it's done. Okay?
Yeah.
Did it answer your question?
Yeah.
Yeah, awesome. It's quadratic complexity, by the way. The shuffling is extremely expensive because you really have the network wire that are on fire at that moment, right? Any other questions? Who understood? Okay, so you deserve your break. So now we are going to take a break. I'll see you at 11:15, and then I'll continue.